What's up, everyone? My name is Omar Othman, and I'm going to be trying to explain the cardiac cycle to the best of my abilities. All right, let's start. So, first of all, let's talk about the blood flow in the heart and the anatomical names of the heart. So, let's start with the right side. At the right side, you have the superior vena cava here, and then the inferior vena cava at the bottom. The oxygenated blood flows into the right atrium, and then you have the tricuspid valve here. The tricuspid valve opens, blood flows into the right ventricle, and then from the right ventricle, the blood flows into the pulmonary arteries, into the lungs. Okay, and then there's a pulmonary valve here. It goes into the lungs, and then now it becomes oxygenated. Now the blood flows into the pulmonary veins, taking the blood into the left atrium. The left atrium here takes oxygenated blood, and then there's the mitral valve here. The mitral valve opens, the oxygenated blood flows into the left ventricle, and then from the left ventricle, the blood flows into the aorta, and here there's the aortic valve, into the aorta, into the rest of the body. All right? Okay. Now let's talk about the cardiac versus the skeletal histology, just a tiny bit. So there's two T tubules. These are T tubules. They're basically like invaginations into the cell membrane, and then in the cardiac cells, the cardiomyocytes, the T tubules are 5 times longer than the skeletal, and in the sarcoplasmic reticulum, and then the sarcoplasmic reticulum is less developed than skeletal. That's what the doctor explained to us. Okay. Then you have the Wigger's diagram. This is what we're going to be talking about mainly today. All right, I'll be going over this slide, but let's go over a couple other things first. The ECG. Quickly, the ECG here, this is the P wave. The P wave is the atrial contraction. Okay, then you have the Q. The Q is over here. From the P to the Q, this is the AV node delay, and then once the delay ends, the ventricle starts contracting. So from Q to R to S is the QRS complex. This is the start of the ventricle contraction, and then at T is when the ventricle starts relaxing. Okay, and this is what you have here. Now let's compare this to the phonocardiogram, which is basically measuring the sounds coming from the heart. Okay, so as soon as the ventricle starts contracting, there's the sound, but this sound actually doesn't come from the contraction. It comes from the closing of the mitral and the tricuspid valves. Let's go back. So these valves over here, once they close, that's what that sound is. Okay, and then there's also another sound here, and this is the closure of the pulmonary and the aortic valves. Right, when they snap back, this is the other sound. The other sounds are going to be mentioned in another lecture. These are the main sounds. So it starts at the contraction, and then the start of the relaxation. Okay, and here it's going more in depth about them. Right. Okay. Now let's talk about the difference between systole and diastole. Right. Well, systole is contraction, and diastole is relaxation. Okay. What is the contraction? What are we talking about? Contraction of what? Well, we're talking about systole. We're mainly talking about the contraction of the ventricles, right? So let's go through this again. Let's talk about the sounds again. All right, the lub is the first sound, the S1, right? Right now our atria have contracted. They're pushing the last bit of blood into the ventricle. As soon as the blood is pushed in, the mitral and the tricuspid valves over here, they snap back, and that's the first sound. That's the lub, right? As soon as the valves close, that's when the ventricle starts contracting, and that's the systole, right? And then the ventricle starts contracting. Now, what is the diastole and what is the dub, right? Now, in this position right over here, we're looking at the ventricle contracted, and it's pushing blood into the pulmonary and the aortic, the pulmonary arteries and the aorta, right? It's pushing blood, and the valves are open. But as soon as they close, right? As soon as they close, that's the sound we're hearing, and as soon as they close as well, the ventricle starts to relax. So that's what we're seeing here. The valves, the pulmonary and the aortic valves close, or they're called semilunar valves because they look like half moons. They close, and that's the sound that you hear. That's the dub, right? This sound and this sound. Okay. Now let's talk about quickly about normal heart rate and exercisation. So when you're exercising, or when you're in normal heart rate first, In normal heart rate, there's barely any sympathetic. There's still some sympathetic There's still some sympathetic activity going on in the heart, but it's very minimal, right? So the diastole and the systole. Let's talk about them. So firstly, the diastole is the start of contraction till its end. So this is it over here. It's around 40% of the ECG of the heart of the beats, right? And then the other 40% is the relaxation, or the other 60%. I'm sorry, is the relaxation, right? So you have 40% systole and then 60% diastole. So the heart is relaxing more than it's contracting. Now this is very important because it allows your heart to relax, right? If your heart is overworking, then your heart is going to get tired and it might cause failure. Okay, so this is very important for that reason. Now let's say you're exercising, right? So when you're exercising, there's no more sympathetic activity on the SA node and the AV node and the rest of the heart, right? That causes the faster action potentials everywhere, right? So faster action potentials means the systole and the diastole are going to be faster. Mainly, the diastole is going to be the diastole is going to be affected. It's going to be shortened by a lot. Now you can see here the systole was pretty long. I lined them up for you here, and this is the normal heart rate. It's pretty long. Systole, it's decreased a bit. But mainly you can see here the one that got decreased the most is the systole. It's decreased here maybe more than half, right? So, and this causes the diastole, the relaxation, to be less than the contraction. So you're working more. You're working 65% of the time now, right? That's going to cause you to get tired. And also, blood is entering the ventricle when you're relaxing. So if you're relaxing less, there's less filling of the ventricle, and that's also going to decrease the cardiac output, how much blood you're giving out every time. All right. So on the Wiggers diagram, we have the relationship between all of these, right? All of these pressures, volumes, and how they relate to the ECG and the phonocardiogram. We already talked about the phonocardiogram and the electrocardiogram, right? But we have still the pressures and the volume. Now you have three pressures. We're talking about the pressures mainly of, this is the left side. We're talking about the pressures of the left ventricle, the left atrium, and the aorta, right? And so let's look at the pressures really quickly. I know the slide is not liked by a lot of people. I don't like it either, but the doctor said that he might bring stuff from this, and I'll try to explain it really quickly, right? So these look like fractions and weird numbers, minuses, what's all this, right? Firstly, this is just the pressures that are occurring normally in the heart. Okay, let's start with the aorta, which is most well known, which is what we're measuring, right? When you go to the doctor and he tells you have this pressure over this pressure, this is what we're looking at here. So in the systolic, in the contraction, you're going to have a high pressure because it's contracted, and it's going to be around 120 millimeters of mercury, which is what we measure in. But it's going to be around 120. So the range is between 100 to 140, and then we're measuring the relaxed pressure. When the heart is relaxed, the pressure of the aorta is going to be around 80, right? And so it's going to be, the range is 60 to 90 in a healthy individual. And so this is what we're looking at. We're looking at systolic over diastolic, okay? And you see how the systolic here was from 100 to 140? Same thing here in the left ventricle. The systolic is going to be 100 to 140. This left ventricle is what's causing the aorta to be this high in the first place, right? So the systolic is the same, and then its bottom, it's relaxed. You see here 3 to 12, it's very different. But actually, when it's relaxed and it's open to the atrium at the same time, the pressure is going to be very low, right? It's relaxed. It's very huge actually. So it's going to be from 3 to 12, right? And then left atrium, we don't really talk about the systolic or diastolic. It's usually between the range. The pressure is usually between the range from 2 to 10, okay? And then you have the pulmonary veins and arteries and whatnot. So the pulmonary artery here is 15 to 30 systolic, and then 4 to 12 diastolic. It's the 15 to 30 systolic is caused by the right ventricle systolic being from 15 to 30, and diastolic is also from 2 to 8. And then the right atrium as well, we don't really talk about systolic and diastolic. It's in the range from 2 to 8. Okay, this is what basically the slide is talking about. Now let's talk about the Wiggers diagram, right? This is the most important part. Okay, let's go through it step by step. Now, you have the atrium, it contracts, right? And when the atrium contracts, it pushes the last bit of blood, the last 20% of blood into the ventricle, right? And then it has a name called primary pumps, right? Without the atria contracting, the ventricle still has enough volume to serve the heart. We don't need the atrial contraction, but it pushes the last bit of blood, and then after it contracts, the atria relaxes. The mitral and the tricuspid. We're talking here about the left side, so it's going to be the mitral valve. It shuts, and as soon as it shuts, the left ventricle contracts. Okay, so we have here the atria starts contracting, and because the atria contracts, the atrial pressure it bumps a little, right? It bumps, and when the atria contracts, it pushes the blood into the ventricle. So the ventricle volume here it increases. Okay, and this is what causes the A wave in the atrial pressure. Okay, the valve closes. The valve closes at the end of the atrial contraction when it starts to relax, and as soon as the valve closes, the mitral valve or the atrioventricular valves close. That's when the ventricles contract, and you can see. Well, we said that the diastolic pressure of the ventricles is around 12, right? And it's the same here as the ventricle. Okay. Okay, let's continue with the atrial pressure. Okay, and so there's this bump, but then after the ventricle has it's contracting, it makes enough force to open the aortic valve, right? And once that valve opens, now there's a little bit more leeway. There's a little bit less pressure on the mitral valve. Sorry, on the mitral valve. So this is why you have the C going down, right? It's this little bump here is called the C wave, right? And then now the atria is relaxed and it's slowly filling up with blood. Slowly filling up with blood that's getting collected from the oxygen blood that's slowly filling up with blood from the rest of the heart. Okay, let me repeat this part. Okay, so you have the ventricle that starts to contract, and when it starts to contract, it's pushing outwardly on all sides and even all valves, mitral valve and the aortic valve. It's pushing them. It's pushing them both, right? And well, this valve, it's like this. It won't open if you push it, right? It might just go backwards a little bit, but it won't fully go backwards. It's still closed, but it might just tend to go back. Tend, keyword, right? And this tendency for it to go backwards increases the pressure in the atrium for a bit, and this is what we're seeing here. It's slowly increasing. Okay. Well, the increase in the ventricular pressure, the ventricle is contracting and it's slowly increasing in pressure over time as more fibers contract until it opens the aortic valve. And once the opens the aortic valve, that's where most of the pressure is going now, is going to the aorta, and there's now less pressure on the atrium on its valve, and so there's this decrease over here that you're seeing. Okay, now the atrium is relaxed. Okay. Slowly, there's blood filling into the atrium. And this is the blood that's collected from the lungs. The oxygenated blood collected from the lungs is going into the atrium. And this is what you're seeing here. This steady slope of blood filling into the atrium, it's called the V wave, right? And it's the slow blood that tends to build up in the atrium until we have the contraction again over here. Not the contraction. Don't worry about this part. Okay. Now let's talk about the ventricular pressure. Now we said that the blood. Is once the atria contracts, that's when the blood is going into the ventricle, right? And okay, now let's talk about the ventricular pressure. So for the ventricular pressure, let's start from the atrial contraction again. So the atria contracts. It's pushing blood into the ventricle. This causes a bump in the ventricular pressure as well, right? And you can see the blood is increasing. It causes a bump in the ventricular pressure. Now the AV valve closes, the mitral valve closes, and as soon as it closes, the ventricle contracts. Okay, and you have to understand that the afterload is basically the pressure of the aorta. It's pressure of the aortic valve. You can't open the aortic valve until you go past this pressure. Right, so it's basically like a threshold that you have to meet, right? Because if the aortic pressure is 80 and the ventricular pressure is 20, blood won't go out. So it has to increase above 80 for the blood to go outside of the atria. And if it goes anywhere below, the aortic valve will go back down. It will close. Okay? So in this period here, the ventricular pressure is around 12, let's say, and it starts contracting, and the pressure is building up. It's increasing. It's increasing. But the valve still hasn't opened. It's slowly increasing here. So the pressure is increasing. The volume of the blood inside the ventricle is still the same. No blood has left it. Okay? And this is called the isovolumic contraction. Okay? So there's no blood leaving, and it's contracting isovolumic. Okay? Until the aortic valve opens. It reaches 80, it goes above it, it reaches the threshold, the afterload, right? Whatnot. And then blood starts ejecting outside of the ventricle, outside of the ventricle into the aorta, right? Now, in this blood ejection, you have two phases: the rapid phase and the slow phase. So in the beginning, you have a lot of blood. You push a lot of blood out with a lot of force. You have a lot of force to push this blood out. Okay, so that's when 70% of the blood is getting ejected. In the first third is the rapid phase. The first third, 70% of the blood is getting ejected because of the most force and the most volume of blood. Now you've used up some of the force, you used up a lot of the blood. In the second 2/3 is when the rest 30% of the blood is getting ejected now, right? And it's called the slow ejection phase, okay? And then you have and then at the same time, because you're pushing out less blood, there's less force, the pressure is going back down. You're filling up the atrium, and the ventricle has lost a lot of its blood. So now the atrium has more pressure. The atrium is now back at the atrium pressure is increasing. The ventricle is now less. It's less than 80, so the valve is going to close. The aortic valve is going to close, and as soon as the aortic valve closes, the ventricle relax. The ventricle relaxes, and at this stage, none of the valves are open again. The AV valve, the mitral valve, and the aortic valve are closed. So it's relaxing. So the volume in the blood in the ventricle is going to be the same. Blood in the ventricle is going to be the same, and the volume is in the ventricles relaxing. So isovolumic relaxation. This is what we have here. Okay, and then finally the mitral valve opens again, and then the volume, the ventricle pressure is around a plateau until the atrium contracts again. Okay. So we talked about the ventricular pressure. Now let's talk how this relates to the aortic pressure, right? So when the ventricular pressure, when there's blood pushing, when there's blood going into the aorta, that's when the aortic pressure is increasing, okay? And that's what we're seeing here. So blood is going out because of the ventricle contraction. Blood is going out, and then the aortic valve closes. Now there's no more blood going in, and you see, it's going up, and this is less. There's now less pressure. It's going a little bit down. The AV valve or the aortic valve closes, but you see here a little bit of a bump. Now, why is there a bump here? Okay, well, when you're filling up the aorta, you're filling it up. It's elastic, so it's going to stretch. It's going to stretch a little, not too much. Has only a little bit of elasticity, but it's elastic. It stretches, and once the aortic valve closes, it now recoils. So all this blood is now pushed back. It's basically like a contraction, but it's not contraction. It's not muscle. It's just recoil from the elastic fibers. So it recoils. Now a little bit of blood is pushed onto the aortic valve, and this is what we're seeing here. This recoiling increases the pressure, and then the blood now is going into the rest of the body. That's why we're seeing a slow decrease is going to the body. It's getting used up, and then it increases again at the next ventricular contraction. Okay, and then we were looking at the volume here. The volume it's increasing because of the AV valve. Increasing because of the atrial contraction, and then here the volume is the same, isovolumic contraction, and then it's decreasing because it's going to the aorta. It's decreasing here, right? Until the AV valve, the mitral valve opens again, right? So the mitral valve opens, and then now blood can go from the atrium to the ventricle. So now the ventricles relax, and you have three phases. The first phase being the rapid filling of the ventricles. Now, why would there be rapid filling? So here, we're talking about the atrial pressure. Why is it increasing? Because blood is slowly building up in the atrium, but the valve is closed. So that's why the pressure is increasing. Now, if you open the valve, now all this blood that's stored in the atrium is now going into the ventricle. So this is why it's rapid, right? So the first third is the rapid filling of the ventricles. Then you have the second third. The valve is still open. The atrium still hasn't contracted. It's still relaxed, right? But there's blood coming from the rest of the body into the atrium, and then the valve is open. It's just gonna go into it. So there's basically a slow buildup of blood back into the ventricle. This is just the blood coming from the body, and then you have the third phase, and this is the contraction of the atrium, right? The contraction, it pushes the last 20% of blood in the atrium into the ventricle, and then basically the cycle repeats where you have the ventricle contraction afterwards. Okay, that's basically everything for the Wiggers diagram. I hope you understood this. Okay. Then we're going to talk about the end diastolic volume, end systolic volume, and stroke volume really quickly. The end diastolic volume is how much blood there is in the ventricle at the end of its relaxation. So basically right before it contracts. And if you look back over here, the end diastolic volume is this, right over here. And this is when most of it is filled up. It's around 120 milliliters of blood, right? And the end systolic volume is how much blood after it contracts, after it's done contraction, basically right before it relaxes. So after the ventricle has contracted and has pushed most of its blood out, there's still a bit. It's never going to be zero. It's never going to push out all of its blood. There's still a bit left, and this is around 50 milliliters of blood. Right? This is how much blood there is at the end of the contraction. Okay, and so if there was 120 milliliters of blood before it contracted, and 50 milliliters after it contracted, how much was lost? It's basically a subtraction. So 120 minus 50 is going to be 70. And this is how much blood went to the aorta, right? And it's called the stroke volume, how much the stroke was. Forget this ESV here. It's not SV, it's stroke volume, SV, and it's 70 milliliters, okay? Now, we want to know how efficient it was, right? There was 120 milliliters before it contracted, and only 70 went out. And this is called the ejection fraction, right? 70 over 120 is how much of the blood that was intraventricle, the percentage of the blood that was intraventricle that went into the aorta. And it's 58%. It's around 60%. That's the normal range, okay? And then you have the cardiac output. The cardiac output is basically just how much blood circulates every minute, right? And how can you calculate that? Well, if you have the heart rate, which is the beats per minute, how many beats there are per minute, which is around 70 beats per minute, okay? So you have 70 beats going out, and you want to contract, and you want to calculate how much blood is in every beat, and we use this. We calculated this with the stroke volume. It's 70. So if there's 70 in every beat, and there's 70 beats per minute, 70 times 70 is 4,900 milliliters, which is around 5 liters. You have to know these numbers. The cardiac output is around 5 liters in every person. So there's around 5 liters of blood getting pumped in your body every minute. Okay? And that's basically it. I hope you enjoyed it. I hope you understood from me, and see you in the next time.